Hello students and welcome to the quick solution of All India Cast Test Series JEE Advanced 2019 Test 3A Paper 1 Code A and B Physics. Let's move to question number 1. In question number 1, a light beam of diameter root 2 r is incident symmetrically on a glass hemisphere of radius r and refractive index mu is equal to root 2. Area illuminated as base of hemisphere is. So let's analyze the situation. So suppose this is the vertical line, symmetrical vertical line, and suppose ray incident at this point. It is given in the question that the diameter of the incident beam is root 2r. So this separation is r by root 2. So this separation is r by root 2. So if I draw the normal at this point, the normal is drawn in this way at this point, and since this is r, then this angle is 45 degree. So if this angle is 45 degree, this angle is also 45 degree. So it is the angle of incidence for the extreme ray. Now if the ray moves in this direction, as it enters the hemisphere, the ray will bend towards the normal. So if I draw, then the ray will move in this direction, and let this is the angle of refraction. So if I apply the Snell's law at this point, I can say that 1 into sine 45 degree is equal to mu, that is root 2 into sine r. So from here the value of r comes out to be 30 degree. So the angle of refraction is 30 degree. Then this angle is 15 degree. Now since this is the extreme ray, in the same fashion the extreme ray of this side comes in this way, and this is the area of the base which gets illuminated. So if I calculate the radius this, let it be represented by x, then I can find out the value of x. So x can be written as r by root 2 minus r by root 2 tan 15 degree from the given geometry. The value of tan 15 degree can be find out tan 45 degree minus 30 degree, and it comes out to be root 3 minus 1 upon root 3 plus 1. So if I substitute here r by root 2 taking common, so 1 minus root 3 minus 1 divided by root 3 plus 1. So on solving this, it comes out to be r by root 2 into 2 times divided by root 3 plus 1. So the area illuminated at the base of hemisphere is pi into x square. So if I substitute the data, it comes out to be pi r square divided by 2 plus root 3. So option C is the correct answer. So the correct answer for question number 1 is option C. Let's move to question number 2. In question number 2, a ray of light enters a spherical liquid drop at angle of incidence I and suffers one internal reflection inside drop. If angle I is adjusted such that ray suffers minimum deviation as it comes out of the drop, then value of I is, and it is given the refractive index of the liquid is root 2. So first of all, I am drawing a spherical liquid drop. Suppose this is the spherical liquid drop. Let the ray incident on this sphere at an angle I. This is the ray incident at this point at an angle I. So if I draw the normal at this point, the normal will be drawn in this way at this point. So this angle of incidence is I. So suppose the ray moves in this direction, then let this is the angle theta, which is the angle of refraction. So this is the deviation delta 1, and it is clockwise. Deviation delta 1 is I minus theta. So when the ray incident at this point and Ti occurs at this point, then if I draw the normal at this point, then this angle is also theta because these two lengths are same. From the same concept, I can say that this ray gets reflected at this point, and then this angle is also theta, and when the ray reaches here, then it comes out of the liquid drop, then the angle of incidence, when the ray incident at this point, then this is the normal drawn. Again, due to symmetry, this angle is also theta, and we can say that if the ray goes out of the liquid drop, then it goes in this way, then this angle of refraction at this point will be I. So if I see the deviation at different points, then the deviation here is delta 1, deviation here is delta 2, and it can be written as 2 pi minus 2 theta. Similarly, the deviation delta 3 is in this direction. It is also clockwise, so it can be written as again I minus theta. So the net deviation is delta 1 plus delta 2 plus delta 3. All the deviation are in clockwise sense, so it can be written as 2I plus 2 pi minus 4 theta. Now in the question it is asked, if angle I is adjusted such that ray suffers minimum deviation. So in order to get the minimum deviation, I am differentiating this equation with I. So d delta by di is equal to 2 minus 4 d theta upon di. So if I substitute the value of d theta upon di by applying Snell's law at this point, then I can say that 1 into sin I is equal to mu into sin theta. So from here, the value of d theta upon di comes out to be cos I divided by mu cos theta. So if I substitute d delta upon di equal to 0 in order to get the minimum deviation and solve the equation, then finally we will get sin I is equal to under root 4 minus mu square by 3, and at this point we can see that it is the point of, and after checking we will find, and this angle I is the minimum angle of deviation. So at this I we will find that the deviation will be minimum. So if I calculate the value I, that is equal to sine inverse under root 4 minus mu square. So the value of mu is root 2. So mu square is 2. So 4 minus 2 is 2. So 2 by 3. So the correct answer for question number 2. So option D is the correct answer. So the correct answer for question number 2 is option D. Let's move to question number 3. In the given figure, there are two thin lenses of equal focal length f arranged with their principal axis inclined at an angle of alpha by 2, where alpha is very small. The separation between the optical centers of the lens is d is equal to f into 1 plus 2 cos alpha by 2. A parallel beam of light at an angle of alpha with the principal axis of lens 1 falls on lens. Location of final image formed is. Since the rays falling on the lens 1 are parallel, so they merge at a point in the focal plane because the angle of incidence is alpha. So if I see this, since the focal length of the lens is f, let this is the focal plane, and at this focal plane these rays get merged. So let this is the point where these rays get merged. Now if this angle is alpha, then this angle is also alpha. Then I can find this separation. Since alpha is small, so I can write this length as f into alpha. Since this length is f, so this separation can be written as 2f cos alpha by 2, and the principal axis of lens 2 is at an angle of alpha by 2. So let this is the principal axis of lens 2, and this angle is given alpha by 2. So if this separation is 2f, then this is 2f cos alpha by 2. It means this image formed by the lens 1 is lying on the principal axis of the lens 2. So I can say that, so if this is the object for the lens 2, then this is the image for the lens 2. So I can write if this is 2f, since f is the focal length, so if object is placed at the 2f, then the image is also formed at the 2f. So this separation will be 2f, and in that case this separation will be 2f cos alpha by 2. So the height of image is same as that of object when the object is kept at 2f. So this length is also f into alpha. So the location of final image can be written as f plus 4f cos alpha by 2. This is the x coordinate, and y coordinate is f into alpha. So this can be further written as f into 1 plus 4 into cos alpha by 2. So option C is the correct answer. This bracket is placed wrong. So option C is the correct answer. So the correct answer for question number 4 is option C. Let's move to question number 5. In question number 5, a proton collides with a stationary neutron and a helium nucleus is formed. For this reaction to take place, proton must have minimum kinetic energy K0. If instead a deuteron collides with a stationary proton to form a helium nucleus, minimum kinetic energy is K1. Then we have to find out the relationship between K1 and K0. So let's analyze the situation. Suppose this is a proton, and let the mass of proton is m, and it is colliding with the deuteron whose mass is 2m, and the deuteron is at rest. Let it is moving with velocity v0, and it have a collision with the deuteron. In this process, a helium nucleus is formed. So in this process, since the elastic collision is occurring, so the maximum energy loss can be written as half into mu, that is the reduced mass of the system, into v relative square. So I can write half into mu into v relative. Now for the second process, this is a deuteron which is moving with some kinetic energy K1, and it have a collision with a stationary proton whose mass is m, and in the process they forms a helium nucleus. So in this process also same helium nucleus is formed. So the delta K for this process must be equal to what we have calculated in this process. So that is equal to half into mu into v relative square. Since the delta K of both processes must be same and the reduced mass of both the processes are same, so we can see that v relative must be same in both the cases. In the first case, if it is moving with the kinetic energy K0, and let at that moment the velocity is v0, then in order to have the same relative velocity, it is also moving with velocity v0. So the kinetic energy K0 in the first case can be written as half into m into v0 square, and the kinetic energy in this case K1, minimum kinetic energy, can be written as half into 2m into v0 whole square. So from here I can say that it is equal to 2 times K0. So option C is the correct answer. So the correct answer for question number 5 is option C. Let's move to question number 6. In question number 6, in the emission spectra of hydrogen-like ions, energies of spectral lines range from 1.22 electron volt to 52.244 electron volt. Let the atomic number of hydrogen-like ion is Z, and the electron in the excited state, and the electron in the hydrogen-like ion lies in the nth energy state. So I can write 52.244, that is in electron volt, is equal to 13.6 Z square into 1 divided by 1 square minus 1 divided by n square. And second equation I can write 1.224 is equal to 13.6 into Z square. So since the electron is in the nth energy state, so for minimum energy I can write this as 1 divided by n minus 1 whole square. So on solving these two equations, we will get the value of Z and the value of n. So the value of Z comes out to be 2 and the value of n comes out to be 5. Further, now the photons of first line of Balmer series are filtered and made to incident on the surface of the metal of work function 5.0 electron volt. Stopping potential for the most energetic electron ejected will be. So the energy of photon filtered for the first line of Balmer series can be written as 13.6 into Z square, so 2 square into 1 divided by 4 minus 1 divided by 9. So it can be written as 7.55 electron volt. Now if I apply the photoelectric equation, 7.55 electron volt is equal to work function, that is 5 electron volt, plus E into stopping potential. So the maximum kinetic energy can be written as E into stopping potential. So from here the value of stopping potential comes out to be 2.55 volt. So option B is correct. So the correct answer for question number 6 is option B. Let's move to the first paragraph containing question number 7, 8 and 9.